A confirmation about the audio, please, guys. If the audio is clear and available, kindly confirm. Thank you. So, hello, a very warm good evening to all of you, and welcome to Baiju's Exam Prep IAS. Welcome to the session of Geography, where today we shall be furthering and continuing our discussion for geomorphology. Now, yesterday we had discussed about the concept about the formation of planet Earth. How is it that the planet Earth did actually come into existence? We did talk about the entire process of formation, which happened around 4.5 billion years ago. And also, we looked at the concept when we talk about the evolution of the planet since its time of formation to the present day. How is it that the planet evolved? We looked at even the giant impact hypothesis, which tells us about the formation of the moon. Then, after that, we looked at the interior structure of the planet Earth, including the direct and the indirect sources, which help us understand and which make us aware about the interior of planet Earth, the structure of the interior. We looked at the various different sources of information, such as asteroid, meteorite impacts, the gravitational and the magnetic field anomalies. Then we looked at the various different layers, their properties, as well as we understood the concept of discontinuities. What are the various different discontinuities? Then we observed the aspect of geomagnetism. And with the help of geomagnetism, we basically first of all understood why is it the case that planet Earth actually subtends its magnetic field and what is the impact of it. We also looked at the fact that the magnetic poles across the planet, they keep on changing, and it is not permanent, it is something which keeps on varying. And that is something which also impacts what we refer to as the auroras, the northern and the southern lights which get created in the higher latitudes. That is again something that we looked at. Today, we are going to talk about first of all, we are going to initiate the discussion with the basic concept of rocks, the classification of rocks, on what criteria are the rocks classified. Then we shall be picking up the concepts of continental drift theory, the convection current theory, the seafloor spreading theory, and eventually all of that, which leads us to the plate tectonic theory. So, today's portion is going to be very important for the point of view of both your prelims as well as the mains examination. From the portion of the rocks, here in prelims, you can expect questions about the basic classifications of rock types. And in the mains examination, you can expect questions basically about the aspect of the basic features again of rock types, along with the concept of rock cycle. So in the portion of rocks, these are the areas from which questions can always be asked from and have been asked from this particular area. Now, rocks are something that we encounter on a day-to-day basis. When we talk about rocks and the types of rocks, the various different categories, and in various different places, the different types of rocks that we end up finding, we basically observe that there is a variation. Not all the rocks that you would have seen around you, not all the rocks appear to be the same. There is a variation which does exist. So here, we will try to understand what that various types of rocks are. So rocks, when we see rocks in general, they are not always going to be uniform in terms of their appearance, in terms of either their shape, their size, or even in their composition. The rocks are made up of various different types of minerals, various different types of aggregates, and they solidify many of the times, and that leads to the formation of the rocks. Now, the entire region of the crust is composed of very hard rocks. So here, when we talk about it, so basically, rocks are mineral aggregates with a combination of properties of all the various different mineral traces which are present that lends the property to a kind of a rock. For example, a particular rock which is extraordinarily rich in iron, that will always indicate some kind of a magnetic property associated. Okay, any kind of a rock which you will see which is very, very rich in iron deposits, they will have that kind of a property. Then a unique combination of chemical composition, mineralogy, grain size, texture. Grain size here refers to what? So when you take a look at any rock, you will, if you look at it closely, it will be made up of small particles, right? So that is the grain size, whether those particle sizes are larger or whether those particle sizes are smaller. If ever you would have seen a rock being broken into many different parts or two or three parts, there also you will find that the particles, they get exposed. So that is the general understanding of the rocks, and they are basically classified dependent upon their formation. That is the broader classification. That is, how is it that dependent upon their classification, the rocks are divided into three parts. First is the igneous rock, then you have the sedimentary rock, and then you also have the metamorphic rocks. Now, what are these? So, when we say igneous rock formation, so these igneous rocks, igneous refers to what? Something to deal with fire, something to deal with very high temperature, hence the term igneous. Now, here, whenever there is a volcanic eruption which happens, that volcanic eruption leads to a spread of molten materials, very hot materials, which we refer to as lava, that spreads over to the various areas and eventually they solidify. So the solidification of the molten materials leads to the formation of a rock, and that is the case of igneous rock. Okay, now here, let's suppose sometimes you can also have a condition. Let's suppose this is the surface here. Now from here, let's suppose the molten materials are coming out and they are spreading out. Okay, let's suppose the molten materials are getting supplied from an underground chamber where you have all these molten materials accumulated. Now the lava spreads over and it solidifies. So when it solidifies, it forms the rocks. Now, depending upon the chemical characteristic of the lava, what kind of chemicals are present in that, what kind of minerals are present in that lava, that becomes a determining characteristic for the classification of rocks also. Now, other than this, you also have another condition. For example, let's suppose the surface is very hard. Okay, it is a very hardened structure. Now, in that case, the molten materials, they try to come up the surface. But because the surface is so very hard, the molten materials are unable to break through. So, the molten materials, which we know as magma as well, so the molten materials, rather than being able to break through the surface, they will start spreading around and they will solidify in various different shapes and sizes. So here, these molten materials, they have solidified in the interior of the surface itself. They have never managed to break through the surface. In the interior itself, wherever they are present, that is where they keep on spreading and they solidify. So this is also an igneous rock. But here, this kind of an igneous rock is formed in the interior of the surface rather than above the surface. So this is also a characteristic of the igneous rock. So igneous rock overall, if you have to summarize this, are the rocks formed as a result of solidification of molten materials. They can solidify on the surface. In that case, they are referred to as extrusive igneous rocks. And they can sometimes even solidify in the interior itself without being able to break through the surface. Now, I hope we are aware, if we are not aware, the molten materials, when they erupt out of the surface, then they are known as lava. But as long as they are inside the surface, these molten materials, they are also what is referred to as magma. So it is magma which basically emerges out of the surface. And that is the magma. When it emerges out of the surface, then we refer to it as lava. Okay. So this is the case of igneous rock. Now, if I ask you a question, that these igneous rocks, will they be able to contain remains of plants, animals, etc.? Will they have the remains of organic matter or plants or animals? What do you think? Obviously, no. Right? Why? Because it is the molten materials which have solidified. These molten materials might have solidified over anything else, but in the rock themselves, they won't contain any kind of fossils or plants or animal remains. That is why these igneous rocks will always be poor in any of the organic matter whatsoever. Having said that, it can happen over a period of time that when the soil gets formed, soil, basically, we will take a look at the formation of a soil at a much later period of time. When you have formation of soil, so soil gets created how? By the breakdown of these rocks. These rocks, they get broken into many smaller parts, and that is how we see the formation, or we experience the formation of soil. Now here, that is why in general, as and when we will take up the topic of soil, you will notice that the soil which is created out of igneous rocks, always they will be very, very poor in terms of their organic matter and the organic content that they possess. So that is the case of igneous rock. Now then, you have the sedimentary rocks. Now, sedimentary rocks, how are they created? So basically, whenever you have any new landform which gets created, a new landmass gets created. Always it will get created as a result of volcanic action. Volcanic eruption will take place, it will deposit these molten materials will solidify, and that will lead to the formation of the landmass. So, first of all, at any place, igneous rock formations will happen. Now, these igneous rock formations, that is why they are also known as primary rocks. Okay, that is why we refer to the igneous rocks as the primary rocks. Okay, now after this, please write below the images you drawn extrusive and intrusive. Do you have a pen in your hand, my dear friend? Do you have a pen or a paper in your hand? Kindly take up the pen and the paper. And if you feel that there is anything that you can forget, rather than simply sitting and staring at the screen, I would always advise you. I hope you understand, this is not a cricket match that you are watching, or this is not a movie that you are watching through. So take a pen and paper. Please draw those diagrams at your end also if you feel the need of it, and write it down. That will help you revise also. Okay, otherwise you will again come into the category of collector of notes and collector of resources. Okay, right? Okay. Now, here, whenever you have sedimentary rock or whenever you have igneous rock formations, for the first time in any place, you will find that igneous rock formations happen. Now, even in India, when new different land masses were created for the first time, they were basically igneous rock formations. Now, let's suppose you have igneous rocks here. Okay. Now, let's suppose these have come into existence over a period of millions of years. Millions of years we are talking about. We are not talking about a short period of time. Over a period of millions of years, it might happen that there will be streams of rivers, etc., which will come into existence. Streams of rivers, etc., they will come into existence and they will start draining from here. Now, these rivers, streams, everything, rainfall activities, everything, slowly and steadily they will weather down the rocks. They will weaken the rock structure from the area where they are flowing, and they will start accumulating these materials, depositing them somewhere. So, over a period of time, let's suppose here in this area, you have the deposition of materials. You have the deposition of materials. Now, these materials, they keep on getting accumulated. They keep on getting accumulated. Loose materials, they will keep on being accumulated. Now, when they will keep on getting accumulated, they might have plant remains, animal remains, everything being drained by that river. In general, in your life, you would have seen, wherever you would have seen the river flowing, you would have observed that the river carries a lot of these sediments. River carries plant remains, sometimes trees also, sometimes animals also, isn't it? Now they will get deposited somewhere. As they get deposited, one on top of each other, that is the process we know as sedimentation. Because the sediments, as they are known as, these sediments, they will keep on getting piled on top of each other. And think about it. Materials are getting piled upon one upon each other. So here, as the materials, they get piled upon one another, let's suppose, as the materials, so they will impose a weight on the lower layers. They will impose a kind of a pressure experienced on the lower layers. The overlying weight will be imposed on the lower layers, isn't it? So the lower layers, due to that weight, they will start getting compressed. That is a process which is compaction. So they will experience, due to the overlying weight, they will experience compaction. Right? They will start getting compacted, more and more pressed. More sediments will be brought over, more compaction will happen. And you would have seen this around your region also, wherever you are living. Let's suppose you see the soil. Now, if that soil, you keep it moist, you water it all along, the top layer of it keeps on getting moist, and some that soil you can dig it out also. But after a point of time, if let's suppose you leave the soil untouched in a region, it becomes harder. It becomes very hard, almost like a rock. So imagine if these sediments are left on their own out there in the nature for hundreds and thousands and millions of years. Owing to their own weight, not only will they get compacted, but slowly and steadily they will start solidifying. And that is when that solidification of the sediments will happen. They will, each of these particles, they will secrete whatever chemicals they have, calcium, sulfate, etc. They will be secreting those chemicals. And let's suppose these grains, they have calcium. If you press them, that calcium will get secreted. That calcium will basically end up sticking with the other particle also. Slowly and steadily, you will have a hardened rock structure, which won't be as hard as the igneous rock itself, but will have a characteristic of the rock. So that kind of a rock, which is formed as a result of that deposition of sediments, deposition over a period of time leads to compaction. Compaction over a period of time basically leads to sedimentation, or rather cementation. Cementation is when they become harder, very, very hard. So I hope we are aware of the English meaning of the term compact. And I hope that compact, cement, that English meaning we are aware of. So they will get compacted and cemented. And that will lead to the formation of a rock type. And that kind of a rock type we refer to as the sedimentary rocks. So when we talk about sedimentary rocks, these are basically rocks formed as a result of solidification of sediments. First of all, deposition will happen, then they will get compacted, then mean pressed together, then eventually they will harden, and you will have a sedimentary rock formation. Now, will they have the remains of organic matter, that is the plant and animal remains? Will these rocks have the presence of plant and animal remains? What does your logic tell you? Perfect? Yes? So they will consist of the remains of plants and animals, even in our country. You have these igneous rock formations in the region of Chota Nagpur Plateau, that is the region around Jharkhand. Bastar Plateau, that is the region around Chhattisgarh, adjoining portion of Odisha. You have the Karnataka Plateau. These are amongst the oldest regions in our country. Now, these were created earlier. Now you had the origin of small streams from these areas, which would deposit materials in between them. That is where, even today, you find the sedimentary rock formations in between these areas. For example, the region where presently river Mahanadi flows, you will have these kind of sedimentary rock deposits which have happened. These are the areas where you even find sedimentary minerals, for example, coal. In between Karnataka plateau and the Bastar and Telangana plateau, there also you'll find these deposits. For example, the Godavari Krishna river where it flows, there also you have such sedimentary deposits which are very, very old, millions of years old. There again, you'll find the evidence in the form of coal. Coal is a kind of a sedimentary rock which gets created due to the trees. Trees, when they fall in a region, they get compressed and pressed over a period of time. That is what leads to the formation and existence of trees. So that is the case of sedimentary rocks. Okay. Is presence of remains only reason why sedimentary rocks have different texture? No. Without river, sedimentary rock is not possible. It is possible. It is possible without the river flow also. Wind flow, wind action, everything can take that into existence. Okay. So that is the case of sedimentary rocks. Now, sometimes what happens, let's suppose we consider a region where you have in this particular area sedimentary rocks. Okay. Here you have sedimentary rocks formation. Let's suppose over the next few hundred millions of years, let's assume there was a volcanic event in this area. And there was such a strong volcanic event that molten material spread over this entire area. Many kilometers thick molten materials, they spread over this area due to volcanic eruption. Now, this will again form igneous rock. Now, this igneous rock will impose weight on the lower layers, substantial amount of weight on the lower layers. They will experience, the lower layers will experience some amount of heat as well. So, when they are exposed, when the existent rock types, they are exposed to heat, pressure in significant quantity, they simply change their properties, their chemical characteristic, their mineral composition. That undergoes a kind of a change. And that change is what we refer to as metamorphosis. And that is where you will experience the formation of metamorphic rocks. It can happen in the case of igneous rock formations also. Igneous rock formations, let's suppose they experience very high amount of pressure or heat. There also, they tend to change their property characteristic and they form a new rock type altogether. For example, limestone. Limestone, a rock type which you use for the manufacturing of cement, for during the manufacturing process of even iron and steel. Now, that limestone is a sedimentary rock. But when that limestone gets compressed over a period of time, when that limestone over a period of time changes its state, it becomes marble. Marble is something that you use for your construction purposes. So, marble is a metamorphic variety of limestone, right? So, that is how metamorphic rocks are basically those rock types where the existent igneous or sedimentary rocks, when they are exposed to high amount of heat or pressure, they change their characteristic, they change their type, and they metamorphose into a different rock type altogether. So, igneous or sedimentary rocks, when exposed to high temperature or pressure, it gets converted to metamorphic rocks. Okay, that is the basic characteristic. Now, here again, you will see that, or you can come to the conclusion that the first type of rocks created are the igneous rocks. That is again one of the reasons why igneous rocks, you always refer to them as a primary system of rocks. Now, when we talk about these, the igneous rocks, let us take a look at each one of them now. So first of all, I want you to take a look at the image. The written portion will take a look at it differently. So in the image, what is it that you observe? You will basically observe that there is a uniformity in terms of what are the constituents of it, uniformity in terms of the constituent materials, isn't it? So that tells you that the molten materials or the molten lava would have solidified at one go and would have led to this formation of this kind of a rock. So igneous rocks, they will have that uniform property. Okay. Now, here also, how the cooling process has taken place, that ends up determining what is the size of these individual grains, individual particles that you see. Okay. How that cooling has happened. Why do I say so? For example, let's suppose here you have a molten material, and listen to this carefully. Let's suppose you have the molten materials which are spreading over an area. Now, if the cooling process takes place very quickly, very quickly, it will solidify. The molecules, the particles, they will start solidifying in their own place. Right. So the grain size will be very small. The particle size will be very small because individual of these particles, they will end up solidifying almost immediately. But let's suppose if the process of solidification takes place very slowly, so that will give the time for the particles to form bonds and linkages with the other ones nearby. Molecular structures will be created. If the cooling process takes place so slowly, it will give enough time for the particles to form a kind of a bond and a kind of a complex crystal size. Right? So the grain size in that case will be larger. So how that rate of cooling has happened, that will end up determining what is the size of the individual grains. So if cooling happens very quickly, if rate of cooling is very high, individual grains will be smaller in size. If rate of cooling is very slow, of cooling is very slow, then what happens? You'll find size of the particles are larger. Okay, you will have larger size of the particles that you will end up observing. So when we talk about igneous rocks which are formed on the surface, that is the extrusive igneous rocks, or when we talk about the rocks which are formed in the interior, as compared to the surface and as compared to the interior, where do you think that the rate of cooling will be faster? On the surface or in the interior? Where do you think the rate of cooling will be faster? Always on the surface. Because on the surface, they will be exposed to the outside temperature, outside atmosphere. So always on the surface, they will start cooling down very quickly, isn't it? So that is the characteristic that you will also derive in the case of the igneous rocks. We'll take a look into it. So igneous rocks are formed through the cooling and solidification of magma or lava. Igneous rocks may form with or without crystallization. They can form either inside the surface as intrusive rocks, which are also known as, when they start solidifying in the interior itself, when magma starts solidifying in the interior, you refer to it as the plutonic or the intrusive rocks. And when you have the molten materials or magma which solidifies on the surface, they are known as extrusive or volcanic rocks. So that is the case of the igneous rock formations. Okay. Now, then we come to the types. Intrusive, they are formed by the solidification of magma in the inside, and extrusive, solidification of lava on the surface. Now, here in the case of intrusive, you'll find grain sizes is larger. Why? Because, or grain size rather, is larger. Why? Because rate of cooling is very, very slow. Very slow. So if the rate of cooling is very slow, means what? Means the particles in the molten state, they have enough time to form bonds and structure with the other ones as they solidify. So each of these particles will be able to form crystalline structures, right? Diorite, granite, pegmatite, these are the examples. Pegmatite is the kind of a rock from which you extract mica. Mica is a kind of a non-metallic mineral which you use significantly in the electrical industry, right? So that is the case of intrusive igneous rock. Extrusive, these rocks erupt onto the surface, resulting in very small crystals as the cooling takes place quickly. Basalt, tuff, pumice, they are examples of extrusive igneous rock. So this is the basic classification. There is other set of classification also based upon the mineral present, the type of mineral present, and also the properties that they will exhibit. For example, if let's suppose the content of silica is high and iron and magnesium are less, so that kind of an igneous rock will be lighter in weight also in comparison. Okay, it will be very light. Some of these rocks you will observe, they have the property they can float around as well. They can float on water as well, some of these specific kind of rocks where silica content is so very silica. So many of us, we are unable to identify with silica. So the sand particles that you see, sand particles around you, that is containing silica. Okay, so in general, majority of the rock types that you see around you, the lighter colored rock types, they will be having high silica content. Now you will also find some of the igneous rocks which are very dark, greenish to dark green, blackish in appearance. These are the rock types where they will be very heavy. There the iron and magnesium content will be high, silica content will be low. So based on the mineral component of it, they are further classified into mafic, ultramafic, and even felsic. But we'll not cover it here. We'll cover it when we talk about the chemical composition of lava, which helps us understand the different types of volcanic eruption which happens. That is where we'll cover it. But here also, if I give you the naming of it, so based upon composition, you have mafic, mafic, Ma stands for magnesium, Fic stands for iron. So high iron and magnesium content. Everything in the written format I will give you at the time when we talk about the lava and the chemical properties of lava. Ultramafic, very dark colored, high density rocks. And then the light colored, where silica content is high, felsic. Okay, low density. So these are the various different types of rocks or igneous rocks based upon their chemical classification. Majority of the continental landmass is made up of these felsic rocks. This is one of the reasons why the continental crust is generally lighter as compared to oceanic crust also. So here, that is the case of igneous rock. So if a question is asked, what are the properties or what are primary rocks? What are their properties? Will you be able to write 100 words out of it, 100, words out of it? Will you have the ability to write out of it? Yes? Good. This was the question which was asked in 2022 mains examination also. Okay, so this is the classification of igneous rocks based upon where they have been formed and then based upon the chemical properties. Now we come to the sedimentary rocks. Now, when we talk about the sedimentary rocks here, first of all, take a look at the image. Now, again, compare it with the image that you had seen in the case of igneous rock, this one. This is of a uniform property, uniformity all around. Take a look at this image. Here you will find various different kinds of materials included. Various kinds of materials included here. What does that tell you? Over a period of time in a region, these materials would have been deposited and they would have been solidified. So sedimentary rocks in general are also considered to be soft rocks, softer rocks. Why? Because they are made up of so many different types of materials, they will have multiple different kinds of weak points, and joints obviously will be weaker. You can break them easily. You can carve it out easily. This is one of the reasons why you will find that majority of the architectural marvels around you that you would have come across, I'm sure all of you would have covered the portion of history in significant detail. And I hope you would have looked at history beyond the fact that who invaded whom, who attacked whom, who killed whom, when, and how great were the freedom fighters. Beyond that, also, you have studied history. So you would have studied all the major architectural marvels that we have. They are made up of sandstone. Sandstone, be it the Red Fort, be it the Agra Fort, be it the mausoleum of Akbar in Sikandra. Everywhere where you find very intricate carvings, it is made out of sandstone. Why? Because it is much easier to carve intricate designs there, because this is a soft rock structure. If ever you happen to visit the region of in Delhi itself, and in Delhi you have the Horse Khas village, which was developed at the time of the Tughlaqs. It was basically a kind of a resort summer retreat for the Khiljis, the Tughlaqs, the entire clans of them. Now, there, if you notice carefully, you would observe some significant variations in terms of architectural design. You'll find the grayish and whitish structures which were constructed at the time of khiljis. They will have minimal designs, hard rocks, still intact, many of them. And then you'll find during the time of the Tughlaqs, the reddish stone, the sandstone, having very intricate designing. Many of them have been broken down over a period of hundreds of years now. So, the grayish whitish design during the time of the Khiljis, they would generally be constructed out of igneous rocks. That is why it would be almost impossible to carve out designs out of them. But if you take a look at the sandstone structures around them, which were created and carved out during the time of the Tughlaqs, sandstone marvels in terms of the designing work would be observed. Now, this is something that the Turkish invaders they learned over a period of time, and obviously that knowledge percolated, and that is something which was imbibed later on even by the Lodhis and the Mughals when they came. The Mughals, almost all the intricate design work that they did, they would basically use the sedimentary rocks, polished sedimentary rocks. They would polish it so that it could have that same kind of shine. And then that is how they would create the wonderful structures. So these are soft rocks. Now, when we talk about basically the sedimentary rocks, these sedimentary rocks, they are classified into various different parts based upon the fact that how is it that the sedimentation has happened. After all, these sedimentary rocks would be created as a consequence of sedimentation. So, based upon how that sedimentation has happened, they are classified into various parts. For example, let's suppose here, okay, by the way, if you have not covered ancient history, modern history till now, please don't, now is not the time to panic. Please concentrate here. I apologize because I mentioned the name of history here. History will be covered. Don't worry about it. Okay? Can we start concentrating now? Because I see many of you panicking, but art and culture is left. It will be covered. Okay, fair enough. Whenever it will be covered, study at that point of time. As of now, can we please concentrate here? Thank you. Now, these sedimentary rocks basically are always created as a result of deposits. But how are the deposits attained in the first place? So let's assume you have an existing rock type. Let's assume you have an existing igneous, sedimentary, metamorphic, any of the existing rock type. Now, being exposed to sunlight, high amount of heat, high temperatures, cold conditions. So, whenever anything is exposed to very high amount of heat, it has got a property to expand. Any material exposed to high amount of heat has got a property to expand. Any material, you cool it down substantially, it has a property to shrink and contract. Multiple repetitions of this expansion and contraction, what will it do to the rocks? It will weaken. Let's suppose rainfall is also happening continuously in that area. It will further weaken. The existing rock type can break, isn't it? Existing rock type can break into many small pieces. They can be carried over and they can be deposited over a region in multiple small fragments. Let's suppose deposited in the form of multiple small fragments. And these fragments then will stack up on top of each other. They will solidify to form a kind of a rock. So this is one of the ways how the sedimentary rock can get created. Then there is another process. For example, if we talk about the formation of rocks such as limestone or iron ore. Now, iron is an element, iron is a mineral, is a material which also comes out during the eruption of lava and magma. We have seen in the case of the mafic and ultramafic, it is rich in iron component. So that is also where you will find iron. But then you will find large iron ore deposits on the surface. That is a result of sedimentary formation. So how is it that iron ore deposits got created on the surface? I'm not talking about the interior. On the surface, how is it that the iron ore deposits got created? So basically, that was an addition. Here, iron ore deposits got created in areas where you had shallow water bodies. Now, in these water bodies, basically the igneous rocks, they had the iron component, some amount of iron component. So the water bodies basically would have taken some amount of that surface material and they would have some amount of dissolved iron, right? But these were not solid particles, but dissolved iron pieces, let's suppose. Dissolved iron pieces in the water. Over a period of time, life evolved. And when life evolved underwater, you had the growth of plants. You basically had the growth of plants underwater. Now, these plants would carry out photosynthesis. In the case of photosynthesis, the plants end up producing oxygen. Now, this oxygen, which would be supplied in water, that would start combining with the dissolved iron. And there, you would have a chemical reaction taking place. That is Fe plus O2 giving rise to Fe2O3. Right? So this kind of a reaction basically would be observed. Now, this would be in a dissolved state. But when iron oxide would get formed, they would start forming solid pellets and solid particles, and these solid particles would eventually get deposited on the ground surface underwater. These would get deposited underwater. And that is how eventually you had iron oxide or iron ore. Now, these deposits, or this eventually would also solidify to form rock formations. But this sedimentation has happened. Why? Because of a chemical reaction. If this chemical reaction would not have taken place, you did not have the formation of iron oxide at all. So these kind of sedimentary rocks, they come into the category of chemical sedimentary rocks. But here also, another example you can take is the case of limestone. Now, again, understand that nobody is going to ask you in the examination, tell me how iron ore was formed, tell me how limestone was formed, but always better if you know. So if you talk about limestone, just like iron ore, limestone would also be formed underwater. So in all the areas that you find limestone today, it tells you that the region would have lied underwater at some point of time or the other in history. And here, underwater, you have various different kinds of species, shell-bearing animals. Shell-bearing animals means those who have shells. For example, crustaceans, mollusks, that is crabs, lobsters, snails, all of them, they have a shell, hard shell around them. What is that shell made up of? It is made up of calcium carbonate. Then take the case of corals, the whitish corals that you have. They are also made out of calcium carbonate. Now, when these animals they die, their body gets decomposed. But what about these shells? The shells will remain. Now, over a period of time, these shells which have been rich in calcium and carbonate, they would form the deposits. One on top of each other. the sedimentation of these shells, corals, etc. would happen. And then they would have solidified. When they would have solidified, they would form that dark grayish limestone rocks that you observe. You find limestone in the region of even Uttarakhand, in the region of Nepal, in the midst of the Himalayas, which tells you the region that we presently call as the mountainous area of Himalayas. At one point of time, it would have been underwater. There would have been a sea. So the sea floor has been uplifted to form the Himalayas. That is why even today in the region of Himalayas, you find the evidence of fossils or remains of animals which have a marine origin. Then limestone is also to be found in the region of Rajasthan, which tells you that in some part of the history, Rajasthan would also have been underwater. That is why in Rajasthan, over a period of time, as this limestone basically gets metamorphosed, it gets converted into marble. Makrana marbles of Rajasthan are quite famous. So wherever you find the presence of marbles means there would have been the formation of limestone there, which means that region in past would have been underwater. But here also, limestone formation has taken place. Why? Because of the enrichment of calcium carbonate and the reaction thereby. So this is again a chemical sedimentary rock. Then, when I talk about, remember I told you that in the region of Indian subcontinent also, you had the Chota Nagpur region, that is the region around Jharkhand, then the Bastar Plateau region, the Karnataka Plateau region. These were created much earlier, around 2.5 to 3 billion years ago. That is when these got created. Now, you had small streams, rivers, which would originate from there, and there would be sedimentation in between. Along with that sedimentation, you had phases where mass die off of trees would happen. Plants suddenly would die in large quantities, obviously, because of harsh conditions on the land. Now, when these trees, with their woody trunks, when they would die, they would get deposited, and there would be further deposits on top of them. These woody materials would get compressed over a period. Now, this is also a deposit of trees, organic matter. These would, over a period of hundreds of millions of years, they would get compressed. Wood is also made up of carbon. So the carbon enrichment would happen. All the impurities would be moved away and carbon would remain. And that would lead to the formation of coal. But that coal, the entire process of formation, is the result of what? Deposition of organic materials and their solidification thereby. So that is a kind of an organic sedimentary rock. When we talk about crude oil, petroleum, natural gas. Now, petroleum and natural gas, how does its formation take place? So its formation is always going to be dependent upon the regions. For example, those areas which at one point of time would have been underwater, under the sea and the ocean. And basically, you had marine animals. When in a same region, let's suppose a lot of marine animals would have died, and on top of that, you had further deposits, and that would have compacted those remains of marine animals without allowing them to decompose completely. Over a period of time, carbon enrichment there also would have happened. And that is where you would have eventually, over a period of millions of years, those remains of animals would have led to the formation of crude oil and natural gas. So even today, in these sedimentary areas, you have the formation or the presence of crude oil. In India, you find the crude oil where? Off the coast of Bombay or Mumbai rather. You have the Bombay High in the Arabian Sea. So there also that event would have taken place. In Rajasthan, you find crude oil around the region of Bikaner. That again means that region would have been underwater. In Assam, around the Jorhat Digboy region, there also you find the presence of crude oil. That region would have been underwater. In Gujarat, you find the presence of crude oil around the Ankleshwar fields. Again, meaning that region would have been underwater. In the Krishna Godavari basin, you find crude oil. Again, means that region would have been underwater, and a lot of dead remains of animals and plants would have, marine animals would have been compressed. So wherever you find crude oil formation, coal formation, etc., organic materials would have been deposited in huge amount. So basically, we have seen that you have had these kind of formations of sedimentary rocks due to maybe the mechanical weathering and breaking of the rocks in their own place, maybe because of chemical reaction taking place, or maybe because of the deposit of the organic materials. So that is the basis on which the sedimentary rocks, they are classified into three types. You have the clastic sedimentary rocks, chemical sedimentary rocks, and organic sedimentary rocks. Clastic sedimentary rocks, they are formed from the mechanical weathering debris, where a rock has been broken in its own place and would have disintegrated and depositions would have happened. For example, sand, the sand formations. Over a period of time, when they get solidified, sandstone is created. Silt. Silt are the silt, when we refer to as silt. What is silt? Are we aware about it? So, silt is basically the region where, or silt is basically the small sediments that you see the river bringing along with it. Very fine, minute, dark grayish kind of a thing that the river brings along. So, that silt solidifies to form siltstone. Then chemical sedimentary rocks. These rocks are formed from the dissolved materials that precipitate from a solution, iron ore, limestone. These end up forming as a result of the chemical sedimentary rocks. Then organic sedimentary rocks are formed from the accumulation of plant or animal debris. For example, coal, dolomites, etc. So this is the basic classification of the sedimentary rocks. Okay? I hope that is understood. At Himalayas, Tethys was there, yes. If Himalayas were underwater, why there is not petroleum reserves like Mumbai? Because Himalayas, they went through multiple different things and multiple different processes and forces, due to which the that kind of a formation could not happen. Okay, and for how long that region would have been underwater? As long as these deposits would have happened, and then after that, when they would have been compressed, maybe they would have risen above water at that point of time itself, millions, hundreds of millions of years ago. Crude oil available in Iran, Qatar, Russia, these areas were also at one point of time, these would have been underwater. Okay, so that is the case of the sedimentary rock and its classification. Now then, we have the metamorphic rocks. What are the metamorphic rocks? So when we say metamorphic rocks, these are basically formed by being deep beneath the Earth's surface, subject to high temperatures and great pressure, or even near the surface if they are experiencing very high amount of pressure. For example, in the region of the Himalayas earlier were still parts of Himalayas are composed of sedimentary rocks itself. But in the case of Himalayas, as we will see, the formation, if possible, we'll take a look at it today itself. As this formation happened, there was a huge compression which was happening. The Indian landmass continues to move northwards. Eurasian landmass continues to move ever so slightly southwards. And that is why the fold happens. And that is why the height of the Himalaya continues to increase. But nonetheless, there is a huge amount of pressure which is exerted. So over a period of time, the sedimentary rocks in the Himalayas, they have been converted into metamorphic rocks. Okay, so metamorphic rocks basically, when you have the existent rock types, igneous or sedimentary, when they are exposed to high amount of temperature, high amount of pressure, sometimes it also happens due to the movement of the land surface. We'll take a look at it very shortly. Due to the movement of land surface, let's suppose some portion of the land simply goes underneath. Mechanical, chemical, biological weathering we will cover in detail, Mohammed. Please don't worry. This is not the end of the process of weathering. Weathering is in the same region. If a rock type gets broken into various different paths, you have, and if it gets broken due to heat or the action of, let's suppose, the rivers, when they are moving, they are breaking the rocks. That is mechanical weathering. We'll cover it in detail. Okay. So here, let's suppose a landmass goes underneath the crust. The crustal movement continues to happen. Why it happens, where it happens, we'll study. But as this happens, sometimes it goes underneath, and beyond a particular depth, the temperature becomes so very high that the materials, they start to melt. These molten materials, then they rise up. They then lead to volcanic eruptions over the surface. So it can happen that the existing crust can go underneath. So there also, they will be exposed to high amount of pressure. They can get converted into metamorphic. Now, based upon their characteristic, you will find that some of the metamorphic rocks, they will give you a property as if they have been solidified in layers. You will have that kind of a layered appearance associated. These kind of rocks are known as foliated rocks. Okay, foliation basically refers to, for example, onion. Onion you would have seen cut and suffered from the tears due to onion. So onion has got various layers. You peel it out, you have multiple layers. So when you have the rocks having different kinds of mineral composition, when they are compressed, all these minerals, they will form their own different kind of a pattern or banded structure, like bands. Those are known as foliated metamorphic rocks. And sometimes you'll find that the materials, they are distributed uniformly, they get solidified and compressed uniformly. They will give you a kind of a non-banded structure, that is non-foliated, right? For example, marble there. So here, if you take a look at it, there are two types or basic classification of metamorphic rocks, that is foliated metamorphic rocks, non-foliated metamorphic rocks. So these are the rocks. Foliated means they appear in banded structure. They are produced by the exposure to heat and pressure, which makes them appear a kind of a layered structure. They will give them an appearance as if they have various different layers. Phyllite, gneiss, these are the examples of foliated metamorphic rocks. Gneiss is a rock which is generally created as a result of metamorphosis of granite. Okay. Non-foliated, uniform appearance. Marble. You would have seen marble. Marble, does it give you the appearance in general? When you take a look at marble, whitish or absolute blackish, isn't it? So that also is what means uniformity. So marble, quartzite, they are example of non-foliated metamorphic rocks. Anjan, do coal reserve areas need to be underwater? Absolutely not, my dear friend. Coal reserve areas do not need to be underwater. Oil reserve areas need to be underwater. Coal reserve areas, wherever you would have had sedimentation of dead trees in bulk, coal would have been formed. I have a very cute question. So I will take that question regardless of whether other questions I take or not. I will take that cute question. And why I say cute, in the sense of all the positive scenario, innocence that is associated here. Why iron ore didn't form rust underwater? So, my dear friend, first of all, please tell me what you understand by rust. The rust of iron that you see, what is rust? Is it that bacteria and fungus comes there and that forms the whitish or that forms that yellowish portion over iron? What do you understand by rust in general? What is rust? Let me know. I will not take your name. Let me know your understanding. What is rust? Rust is basically oxidation of iron oxide. So when you have iron, you expose it to the outside atmosphere, it reacts with oxygen. The outer surface reacts with oxygen, and then iron oxide is formed. That is rust. But if I am telling you that underwater, automatically you have iron oxide because of oxygen present in water and iron, it will be iron oxide. It is so when you think about iron ore, I hope somewhere in our mind we don't have that preconceived notion that iron ore is that shining iron pieces. People dig it out from the ground, they take it to the construction sites, and they start erecting that iron itself. Iron ore is basically a kind of a impurity of iron, right? From that, you have the smelting process from where you extract that iron. So that is why there is no question of rust getting created in the case of iron ore. Okay, right? How sandstone gets created? Sandstone gets created by the solidification and deposition of sand particles that you see, right? So, are you guys forming a group and asking these kind of innocent questions, or these questions are really, I mean, and don't mind, okay, so quartz is also a type of watch and also a rock. How? Okay. So, I don't know how to answer this. So, basically, when we talk about quartz is a kind of a rock, quartz is a kind of a mineral. From that, you name a watch, you name your child quartz. Does that mean that quartz is also the name of a human and also the name of the rock? How is it possible? You name anything. Quartz as a rock, as a mineral, that shiny small particle, that is used in watchmaking also. It is from that that you have these particular uh, name which is given, but it is a company. I hope you are aware that it is quartz is a name of a company. All the watches, they are not named as quartz. I hope we are aware of that. Okay, right? Okay. How these layered structures are formed in the foliated rock? Basically, see, when you have various different minerals which are present, various different types of deposits that you have, minerals which are present. Godavari, you have a question, which rock is dominant in the world? So it depends. If you talk about the entirety of the crust and the upper mantle, it will always be igneous, and in the lower portion of the crust, metamorphic. But from one region, for example, in the northern Indian plains, you won't find igneous rock at all. You will find only the sedimentary rocks. So here, when let's suppose, Vaibhav, you have the presence of various different types of minerals here. If this rock type experiences compression, it can happen that after a result of that compression, these develop into a kind of a banded structure. That means foliated. Okay. Same condition in both folded and non-folded? No, there is a slight variation in terms of temperature and the pressure also. Not every place will experience the same pressure. In certain areas, let's suppose pressure will be acting from all sides. In certain areas, pressure will be acting only on two sides. In certain areas, you will also have that on one side pressure is acting at this level, in other side pressure is acting at a higher level. So there will be a variation in types of pressure. That is why. Okay. Fair enough. Can metamorphic rocks turn into sedimentary rocks? Absolutely, yes. And that is the concept which we talk about in the case of rock cycle. Is the temples were built with igneous rocks? Not all the temples were built with the igneous rocks. You have many temples which have been built with the sedimentary rock formations. Take a look at the earliest available evidence of the temple, the modern day temple, which is the period in which the earliest evidence of the temple is found. Let me test your that kind of a trivial knowledge if you're asking about temples. In which is the earliest evidence, known evidence for the temples? Much earlier than the Cholas also. Do you have evidence of the Harappan temples till now? Random guesswork is going on. Okay. Taj Mahal is an architectural structure. Marbles on Taj Mahal, that is metamorphic. But then inside the brickwork, etc., many of them are sedimentary also. So basically, when you study art and culture in detail, you will find that you have the earliest evidences in the form of during the Guptas, the 5th century AD. You have that is the remnant of the earliest complete structure of a temple that is made out of sedimentary rock. So temple architecture, both of them you will find. Majorly sedimentary rock formations you will find. Okay. Right, like foliated metamorphic, even sedimentary also have layers. With what is difference? But in the case of sedimentary, it is not always going to be in the banded structure. In the case of sedimentary, you can have a mixture of them together. Here you will observe fixed bands associated. But when you take a look at sedimentary, can you associate any layer here? This is sandstone. Can you associate a layer here? No. Right? Now we come to the rock cycle. What is rock cycle? So basically, we'll talk about it mega slowly. We take it slowly. We'll talk about it. Rock cycle. So an existing rock type, when given with adequate amount of conditions, when provided adequate conditions of temperature, pressure, etc., one existing rock type can always get converted into another rock type. Okay. That process is what is known as the rock cycle. One existing rock type can always get converted into another rock. For example, take the case of metamorphic rock. Metamorphic rock in itself is created how? Maybe an igneous rock undergoing heat and pressure, or a sedimentary rock experiencing heat and pressure. That is how metamorphic rock gets created. But let's suppose this metamorphic rock is exposed to conditions of rainfall, conditions of river action, heating, cooling. It disintegrates, it breaks. It will lead to the formation of sediments. Those sediments, as a result of weathering, erosion, you will have sedimentary deposits. These sedimentary deposits, due to compaction and cementation, will lead to the formation of sedimentary rock. Maybe that sedimentary rock breaks and disintegrates again to form sediments. That can happen again and again. But then it can also happen, for example, in igneous rock, a hard igneous rock structure, that can get disintegrated due to weathering and erosion into sediments that can again get converted into sedimentary rock formations. Or let's suppose the metamorphic rock formations, they eventually they sink underground. As I told you, beyond a particular depth, they will form magma. That magma might rise up and eventually might cool down to form extrusive or intrusive igneous rock formations. Those intrusive and extrusive igneous rock formations that can again move down. Again, it can come up. Recirculation keeps on happening. So each of these rock types, they have the ability to get converted into the other rock type if those necessary conditions are provided. That is rock cycle. So, does not mean that if you have an igneous rock, that region will always have only igneous rock. Over a period of time, it can happen that sediments might be deposited over that region, or that igneous rock might have the weathering of that, physical breakdown of that. Sedimentation can happen, sedimentary rock can form over that sedimentary rock. Maybe it gets deposited so much of pressure it can get converted into metamorphic rock. So one rock type can always get converted into other rock type under the prevailing conditions of temperature, pressure, outside forces. That is the condition of rock cycle. Okay. Now, then we talk about, yes, a sedimentary rock can also disintegrate into sediments. Why not? Now we come to the portion which will determine your entire understanding of geomorphology, which is one of the basic key areas when it comes to your understanding of geomorphology. Igneous to metamorphic, my dear friend, how is sedimentary going to get converted into metamorphic? Vaibhav, let me know. How is it that sedimentary will get converted into metamorphic? Are we aware? Just like sedimentary rock, by cementation, it will get converted into metamorphic. No, metamorphosis is when you have the existing rock types, igneous or sedimentary rocks, when exposed to high temperature or pressure, it gets converted to metamorphic rocks. So either the igneous rock or the sedimentary rocks or the metamorphic rocks, when they get exposed to high temperature and pressure, they change their state into the kind of metamorphic rock. Is that understood? Understood? After igneous rock erosion is it's taken away by rivers and by depositing from sedimentary rocks, then to metamorphic rocks. But how it can be returned to the igneous rocks? It gets returned. I will tell you. Don't worry. Wait for this module to get over. Automatically after that, I will ask you the same question. You would have understood by that point of time. Wait. Yes, it can take millions of years for formation. So this is the portion which is very, very relevant and important and will lay the bulwark for your understanding of the other portions of geomorphology also. Here, in this particular portion, we are going to cover various different theories. We are going to cover continental drift theory, then convection current theory, then seafloor spreading theory, and then eventually plate tectonics theory. Okay. Now, all of these are important for your mains exam. This is the portion which can be relevant both for prelims as well as mains. As well as mains exam. Okay. So, first of all, let me put it very clear. These theories have been provided almost a century back. Continental drift theory was a theory which has been provided almost 100 years, more than 100 years back. Convection current theory was provided in the 1920s. Seafloor spreading theory was provided in the 1950s. And all this led us to the formulation of the plate tectonic theory. Plate tectonic theory is the theory, the modern theory, which suits and fits the scenario, which helps us understand what happens on the ground surface. So when you study the continental drift theory, it will have its drawbacks, it will have its lacunae, it will have its limitations. When you study the convection current theory, it won't be able to explain everything. When you study the seafloor spreading theory, it will also have its drawbacks, lacunae, etc. All of these drawback, lacunae, etc., that has limitations. They have helped us to formulate eventually the plate tectonic theory. So when you take a look at the limitations of continental drift theory or the seafloor spreading, please don't judge it with the present day conditions that you see around you. Because obviously, these theories have not been accepted significantly, but each of them have laid a foundation for our understanding. Maybe a theory is wrong, maybe a theory is not completely correct, but it lays a foundation which helps you understand the world better. That is why you study all these theories, because all of them help the scientists to formulate the plate tectonic theory. Having said that, we start first of all with the basic premise of the origin of continents. What do we mean by this? So, cartography, or knowing the world map, and the ability to have that idea and the image of the world map, that is something which was prevalent for since around 1800s onwards. That is something which was prevalent. But since that point of time, mankind has always wondered that how is it that these continents have this particular kind of a shape? Why is it that the northern hemisphere is dominated by land masses, whereas the southern hemisphere is dominated by the oceans? So that kind of intrigue has always prevailed. That has always been in existence. But in the 1800s, our knowledge of the world was so very limited, it was so very restricted, that basically, when you would take a look at the various different geographers, celebrated geographers of that point of time, all of them, they would postulate a kind of a random concept that, you have more land in the northern hemisphere, less land in the southern hemisphere, because the planet is shrinking, because the planet is cooling down. Mountain formation takes place because the land is cooling down, so there is formation of wrinkles. So there was the entire era of the geographers which we refer to as, we put them into the category of contractionists. They would always adhere, they would always articulate and advocate the contraction of the planet. And they would hold forward the argument that contraction of the planet is actually responsible for the formation of various features of the world. Obviously, they couldn't have been more wrong. But at that point of time, you did not have any competing theory which could provide them correct, or which could basically prove them incorrect. Now, in this backdrop, you have to understand that with the onset of the 20th century, that is in the 1900s, at that point of time, the era of scientific discoveries that reached the pinnacle. Yesterday also we talked about the fact that 1700s and 1800s would be the era where people would go out to different places, they would experience different places, they would have the records of different areas. But the encapsulation of everything and formulation of theories, be it of the universe, be it of the ground surface, be it of the interior of the planet, that started happening in the first couple of decades of the 20th century. The first pioneering theory about the Earth's surface, about the shape of the world, was the continental drift theory. So, that is the first theory that we are going to cover, and then we shall be moving ahead with the other theories also. But before initiating the discussion, I want to take up the discussion in one go. So, we take a break for 15 minutes. We'll be back and we will be continuing the discussion. Okay, so take a break for 15 minutes. We come back and we talk about the theories. Okay. Apologies for the delay, guys. There were some inordinate issues, unavoidable issues, which had to be taken care of. So, is the audio available? Audio and video, right? Okay, perfect. Can we continue now? Okay, right. So, basically, we were talking about the origin of the continents, the position of the various different continents. Where does the position, or what is the present situation and the positioning of the various different continents which exist? So, we had an entire era of geologists who basically adhered to the fact that the mountain formations, the kind of oceanic formations that we see, because this question has always prevailed in the mindset. I'm sure you would also have the same kind of curiosity. Why is it that certain areas are so very deep? They basically form the deepest of the oceans. Why is it that some areas are so very high? They end up forming the tallest of the mountains. So, you had some of the very weird kind of concepts being provided earlier, where the planet is contracting, etc. In 1900s, that is in 1907, for the first time, you had an American geographer with the name of F.B. Taylor. Now, F.B. Taylor, for the first time, talked about the fact that you know what? The continents that we are standing upon, that is moving. Now, right now, it will be, in a way, unwise for us to judge them on their kind of a judgment, or to have an opinion on that judgment, that why were people so very much against that idea that the continents could move. But think about it. A random individual, you pick it up, random individual around you, who would have from their childhood days observed the tallest of the mountains, and who would have witnessed the ground surface as hard it is, and tell them that the ground underneath them is literally moving. That obviously would not be a very acceptable thought, would it? But then F.B. Taylor, when he provided that idea that, the continents can drift, there came another group of geographers who were different from the contractionists, who were known as the drifters. And think about it, drifter basically is not used in a good parlance ever. So they were used, and that term was used as drifters to indicate those kind of people who believed that something could move, the land underneath them could move. But F.B. Taylor did not develop this concept. He simply provided this idea and he vanished into the thin air. Then, by that point of time, during the 1700s, during the 1800s, you had a lot of people who were talking about the fact, who had the records of all the ancient plant and animal remains. By that point of time, enough research had been done into the type of rocks so that we could understand when a particular rock came into existence, what was the origin of various different kinds of rocks, etc. Now, you had a German meteorologist or a climatologist with the name Alfred Wagner. Now, Alfred Wagner, he was a German climatologist. And at this point of time, you also have to be aware about the global geopolitics which played out. Because acceptance and rejection of theories at that point of time always was also dependent upon the global geopolitics. Think about it just as an analogy, I'm providing it to you. For example, in today's world, let's suppose a scientist from Iran, let's suppose a scientist from China, or a scientist from Russia provides a particular theory. There will always be doubts which will be casted upon that individual, that I don't know whether that theory is reliable or not. I don't know whether that person is saying the correct things or not. You will cast doubts and aspersions upon that person. But let's suppose the same thing is talked about by an American scientist or an American physicist. You will have a kind of a trust associated. Alfred Wagner was a German climatologist belonging from Germany, and Germany at that point of time in the early 1900s obviously was one of those which was not taken in a good light by the Western scientific world. So, what was the specialty of Alfred Wagner was basically he specialized in studying how over a period of time the climate across the planet has changed. Alfred Wagner was well known for frequent trips that he would take to Greenland. And in Greenland, what he would do was basically he would dig out the ice samples, and these ice samples would contain the climatic records of the past. And that is how he could formulate that, millions of years ago, the planet across or the planet had experienced this kind of a climate. Presently, the climate is like this. So he studied the change of climate. That was his specialty. He had no specialty or no special idea about the interior of planet Earth, about the functioning of the continents, the movement of the continents, etc. He was not well aware of that. Now, as the story goes, that on the eve of Christmas, one fine day, one of his friends, Alfred Wagner's friends, he gifted Alfred Wagner a detailed world map. Now, it was quite rare in those days. Presently, world map you find at the back of the page also. At the back of the book also, you find a world map. But that was not the case at that point of time. A detailed world map was a rarity. So he was gifted a detailed world map. Now, when Wagner took a look at the world map, something struck in his mind. He observed that the shape of the continent here, the shape of the continent here, that appears to be very similar. It cannot be a sheer coincidence. Let's assume it is a coincidence, but the shape of the landmass here and the shape of the landmass here again is very similar. Then the shape of the landmass across the western part of India and the shape of the landmass here and the characteristic features of it, they are similar. So, like that, Wagner basically looked at various different data pointers which were available. So, after looking at the world map, he was intrigued. And somehow he was convinced that, you know what? The only reason that different portions have a similar land pattern or a similar shape, the only reason that could have been possible would have been because all the land masses would have been one at a point of time and they had drifted away. That is where continental drift, the term, came into existence. In a way, he was much more radical as compared to F.B. Taylor. F.B. Taylor, the poor chap, had only said that, the land masses could move, that's it. Wagner then started studying the evidences in order to understand that is it possible that the land masses could have drifted away. He looked at the geological records of various different places. He looked at the fossil and the evidence of the ancient plants and the ancient animal remains. And he started looking at that. And basically, he arrived at a certain set of evidences. All the evidences pointed to the same direction. And with the set of those evidences, he postulated what is the continental drift theory. Now, the continental drift theory in itself basically was very simple. It talked about the fact that at one point of time in the history of the planet, around millions of years back, you had a giant supercontinent. That giant supercontinent was Pangaea. These are German names, obviously. And he said that it was surrounded by water from all sides. And that is what he named as Panthalassa. That is the ocean of the world. Now, he said that even the present day Pacific Ocean is nothing but the remnant of this Panthalassa. All the other oceans that you have seen, they have been created in between. So he said that look, this Pangaea actually broke. This Pangaea broke into two parts initially. It broke into two parts. In the north, you had a giant landmass which included the present day continents of North America, Europe, and northern part of Asia. He named this as Angara land or Laurasia. And then this Pangaea had the southern portion of it as well. Basically, that is what he named as Gondwana land. You know, this Gondwana land, the name is derived from the Gondwana region of India. Gondwana region is where you find the Gond tribes in India. Because the rocks, they represented a kind of a similarity of structure. Hence, the name Gondwana land became prominent. And that would include the region of South America, Africa, India, even the Arabian Peninsula, Australia, many of these islands, and Antarctica. That would form the Gondwana land. He said that the continents have drifted and formed this. Then, after that, it further disintegrated, it further broke down. And as it broke down, it basically had this westward movement where North America and South America, they moved west. They broke and moved to the west. Then the other portions, if all of them were joined together, the portions, they started moving northwards. And that is when India, which was at one point of time joined in the region around Antarctica, it covered that distance and moved to the present place. Africa moved here. South America moved here. Australia moved here. So he said that, look, there are two kinds of movements that the continents are experiencing: the westward drift and the movement away from poles towards equator. These are the two movements that the world is actually witnessing, that the world is presently experiencing. But then, when we talk about specialty, specialty in a subject is very important if you have to go into the details of it. Wagner's specialty was to study climate change. He did not have any clue about the interior of the planet. He did not have any clue that if I'm saying that the lands are moving to the west, why they are moving. But all the evidences that he had, it pointed to the fact that the land has moved. And we will take a look at the evidences. But when it came the time to support that aspect, provide reason for that aspect, the reasons that he cited were so very inadequate that basically the entire concept of drift was ignored, it was rejected. Wagner, in fact, published his theory in the form of a book, in the form of an essay, what is referred to as the, or it was the book which was basically published in 1912. And that was a book which was published in German. So obviously, it was not available to the wide world. It was something which was not available to the wide world around him. The world got the English translation of that in the early 1920s, because the 1910s, that was the era of war. That was the era of First World War, right? So obviously, the German translations won't be easily available. Now, that is when eventually you had the case where in 1920s the world was made available of the translation. That is when the American geologists, the American scientific community also studied that. And they laughed at Alfred Wagner. That look at the reasons that he has said, reasons for the shift of the continents. That is absolutely ridiculous. That is stupid. Wagner was made fun of. Wagner was ridiculed. He was banned from various scientific communities. They, in fact, even convinced F.B. Taylor to issue a public statement at that point of time that, look, I have got nothing to do with the continental drift theory. I only said that the continents could move, but Alfred Wagner is saying something which is very stupid. Alfred Wagner was ridiculed, ostracized. The continental drift theory was rejected. But it was only decades later, in the late 60s and 70s, when more scientific data became available, when Alfred Wagner was vindicated. Obviously, he was long dead by that point of time. It was during one of his sojourn trips towards Greenland. That is when he basically died. Again, he left all this theory and he started continuing his study of climate change. That was his specialty. He started continuing that. And Alfred Wagner basically died as a person who was defamed at that point of time, who was ostracized at that point of time. It was only many, many decades later when Alfred Wagner was proved correct that yes, the continents indeed are moving. But then, here, we are going to study about the evidences which convinced Wagner that you had that Pangea and it moved. All those evidences are correct. But then we will also take a look at the reasons that Wagner provided, on the basis of which his theory was ultimately rejected. Now that we are wise enough, now that we know more about it, we can say that continental drift theory laid the groundwork in terms of the imagination that yes, the continents could move. It laid the groundwork, it helped people understand that yes, indeed, the continents could move. So, the first person who can imagine that, you have to give credit to that person. For example, the in the present day, when you think about it, the airplanes can fly. All of us, we know that. So, you, let's suppose tomorrow you devise a new kind of an airplane, fair enough. You are a good intellectual, but always credit is given to the Wright brothers. Why? Because they were the first ones who thought about the airplane. They invented the airplane. So, similarly, in the geographical community, while the entire world was talking about the fact that the planet is shrinking, here was a man who said that no, planet is not shrinking. You have the world which is actually drifting away from each other. So, Alfred Wagner presently is given a lot of credit in terms of our understanding of the entire world. So, here, when we talk about it, we will study the various different evidences. What are the evidences? What are the reasons why this theory was eventually rejected? Okay. Placer deposit is also an evidence. Good. See, some people are so very smart. Placer deposit and all, you know. Very nice. Okay. Let us assume we don't know everything, right? And let us start with our understanding. First of all, his basic idea which struck was that all the continents, they have a kind of a jigsaw fit, right? They appear to fit in a kind of a jigsaw puzzle. So here, all the various different continents, they appear to have, Vaibhav, don't worry, I'll tell it in detail, don't worry. So here, all the various different continents, they appear to make a perfect fit. That cannot be a coincidence. It can be a coincidence in some region, but it cannot be a coincidence in all the other areas. So this tells you that at one point of time, this would have been together. This would have been a unified landmass. Then, furthermore, he looked at other evidences of geological rock formations. When a rock gets created, igneous rock formations happen by the method of radiocarbon dating, etc. You will be able to calculate the age of the rocks also, right? So he found out that the rocks in the region of the Appalachian Mountains here and the rocks in the Scottish Highlands, they have the same origin. They have the same geological patterns. They have the same mineralogy and the same time period. It cannot be a coincidence. It cannot simply be a coincidence that everything is same tens of thousands of kilometers. Similarly, he observed that the rocks here in the Brazilian highlands and in the region of Africa, they have a similarity. So basically, again, that cannot be a coincidence. So Wagner basically concluded that, look, at one point of time in history, North America was joined with Europe, South America was joined with Africa, and these continents have basically moved in the westward direction. Then, if we take a look at these geological evidences, similarity of geological structures across continents, and presence of similar mountain ranges across North America and Europe, Appalachians of North America, they are similar to the Scottish Highlands, similarity of geological rock structure in Western Africa and South America. Okay, then he also looked at placer deposits. What are placer deposits? Placer deposits, what are they? So basically, in an area, let's suppose here, you have a river which is moving. Okay. A river which is moving. Now let's suppose here you have a kind of a mineral which is not soluble in water, which remains insoluble in water. Let's suppose here you have a kind of a mineral. Okay. Now in this mineral, let's suppose we take the case of gold. Gold is not soluble, right? It is insoluble in water. Now, this water will carry these gold particles along with it. Slowly and steadily, it will erode those gold particles. It will carry it along with it. And it will deposit these particles somewhere here. Now, these deposits have been brought away from a far away place. And it appears as if they have been placed in this region. Okay? So these are what you know as the placer deposits. And this is what is known as the source rock. Because these deposits have taken place, these deposits have happened because of the erosion of the source rock. Okay. Now, in the western part of Africa, you find these gold deposits here. You find the gold deposits. But the source rock for these gold deposits were not to be found in the region of Africa at all. These were simply deposits. So the geologists always wondered where these gold deposits have come from. What is the origin of these gold deposits? Upon further investigation, it was found out that the source rock lies in the Brazilian highlands here, in this area. Now, how can it be possible that tens of thousands of kilometers away, You have the deposits which have been created. You have the deposits which have been created at such a far away place. How can it be possible? So that is where, again, he concluded that these would have been at one point of time unified, and they have now drifted away because he was convinced that South America has moved westward from the region of Africa. So placer deposits also hold an indication, right? So when we say placer deposits here, so minerals insoluble in water can be carried away by the rivers and streams and can be deposited at far away places, and that is, these deposits are placer deposits. Evidence supporting drift basically, you can have gold deposits of West Africa has got source rocks in South America. Okay, gold deposits of West Africa have got the source rocks which were situated in South America in the region of Brazilian highlands. So this was again one evidence. Another evidence was the glacial evidence. So wherever a glacier moves, wherever you have or you experience the movement of glaciers, in those areas, you will end up finding in the region of the glacial movement. Glaciers, by the way, they are massive, massive blocks of ice which are moving. So the force exerted by glaciers are oftentimes unparalleled. So wherever a glacier has been in motion, it will leave behind evidences. Those evidences cannot be left behind by a river movement, by wind movement. They will not create such kind of impact or such kind of evidences. So such glacial evidences were to be found in the region of India, significant portions of India, southern part of India. They basically have the ancient evidences which indicate that glaciers would have been in motion there. Southern part of Africa, South America, Australia. All of these basically had evidences that you had glaciers in existence in these areas. Now, obviously, this in the present day scenario, it is hard to imagine that in southern part of the country you can ever have the movement or the existence of glaciers. It is very difficult to imagine that Africa could have the movement and existence of glaciers. Very difficult to imagine that South America could have existence of glaciers. So basically, upon taking a look at the geological structures, he found striations. Striations are the linear markings of sorts. They are the linear markings of sorts. So such glacial striations or such kind of linear markings on the ground surface that can be created only if that region has experienced a glacial movement. Observe this. It can be created only in an area which has experienced significant glacial movement. Only in those areas you will experience this striation. These striations were observed in the areas of southern India, in the areas of, for example, Africa, etc. For example, I'll give you an example. I hope that doesn't confuse you. We have coal, significant amount of coal in the river valleys of Godavari, Mahanadi, Damodar, Krishna. We have significant amount of coal. Now, beneath that coal, the rocks which are in existence, those rocks have a glacial evidence or a glacial structure formed. So that means before that deposit would have happened, which had led to the formation of coal, before that, the regions around the present day area of Chota Nagpur Plateau, around the region of Godavari, Krishna, etc., they would have experienced glacial movement. And also, wherever a glacier moves, it erodes the rocks, it scratches the surface. Very tiny particles are eroded and moved from the rocks. And these tiny particles eventually will get deposited somewhere else. So, those tiny particle deposits that you associate, that is what is known as glacial till or tillite. Tiny particles which are deposited by glaciers. So, glacial striations and till or tillite deposits were found in peninsular part of India, Africa, South America. Striation, the meaning is straight sinuous lines. So the striations, these are your striations which get created. And Australia. Now here also an explanation could exist that what if in the previous ice ages these regions would have been frozen and now these regions have basically melted down, so ice has melted down, so you don't have ice anymore, right? That can be a kind of an explanation for that. But even during the ice ages, India never, in the present location of India, freezing did not happen in the tropics. Freezing basically happened in the temperate areas. The tropics considerably remained ice free. So that basically meant that the climate of the planet has not changed so drastically for a very, very long period of time. Right? So he looked at these evidences of the regions which experienced glaciers. It did not make sense to him. But then, if you put them all together, that is when it makes sense. If you put them all together, that makes sense. So he said that, look, at one point of time, all these were present in the region of South Pole and they have drifted apart. So this helped him to formulate a kind of a movement again. That is, movement of the continents away from the poles. Movement of continents away from poles towards equator. But as I told you, Wagner carried out a very detailed study. He did not limit his study only to a certain particular criteria, only to a certain particular set of characteristics. Wagner carried out a detailed study even of the fossil records and the remains of the fossils. He found out certain types of fossils which basically are to be found in areas spread across the world. For example, Mesosaurus. Mesosaurus is a freshwater reptile, right? A reptilian species. It would be of the length of around 8 to 10 feet, and it would exist only in fresh water. The fossils of Mesosaurus were to be found in South America also, in Africa also. How is it possible that the regions which are separated so significantly by thousands of kilometers of sea, how is it that a freshwater reptile can move into the region of Africa? Impossible. Lystrosaurus. Lystrosaurus was one of those species which survived many mass extinctions. Lystrosaurus was very unique, in the era where the reptilian large reptiles would dominate millions of years ago, when you had very large animals, very large anthropods. For example, present day, when you take a look at worms, for example, the worms, the millipedes, the centipedes, they appear to be very small. You can hold it up in your fingers, wrap it around, throw it like a ball also. That is how innocuous they appear. Imagine an era where these insects, millipedes, etc., they were of the size of 2 to 3 meters. So in that era where the you had very, very large reptiles, dinosaurs had still not come into existence. Now, due to various events of volcanic eruption, etc., you had almost all the species which went extinct. Lystrosaurus remained because Lystrosaurus would dig burrows into the ground and it could remain. But the fossil remains of Lystrosaurus can be found in Africa also, India also, Antarctica also. How is it possible that in these faraway places you can have simultaneous existence of this Lystrosaurus? How is it possible? Cynognathus, again, a land reptile. You find it in various areas. Glossopteris, ferns and plants, you find it in large areas. So that is where it was very baffling. Now, it goes against the entire theory of evolution. Theory of evolution tells us what? Theory of evolution you would have studied. Charles Darwin provided that theory of evolution, that species, they come into existence, they basically evolve, adapt, and then they spread out. You cannot have simultaneous growth of species in, or simultaneous evolution of species in different areas. The same species will spread out. The same species will move to different places. Right? So, these fossil evidences, what is referred to as the paleontological evidence, this is what is paleontological evidence. This also pointed out to the fact that everything would have been unified, it simply moved away. Cynognathus was 3 kilometers long inside. 3 kilometers long? It is 3 meters, my dear friend. Can a species be 3 kilometers long in size? Again, the innocence. Okay. So, slow claps for you that for a brief moment you imagined a species which could be 3 kilometers long. So from my side, I can simply appreciate the level of immersion that you have put into the subject. Very good. So basically, these were the evidences which all tell us, which all told Wagner that everything was together and it simply moved away. Now, till now, it makes sense. It would make sense to you also that, okay, that this is what would have happened. Now, when you provide a theory, you need to provide the reasons. Why do you believe that this is happening? This is where things started to go wrong. So, what was the theory exactly? The theory was that you had this large Pangea, which was surrounded by Panthalassa. It drifted away, it moved away, and you have the westward drift of the continents, two kinds of motions. Or all their species of dinosaurs? No, Dhruv. Many of these species that you see, they have been in existence much before dinosaurs as well. Dinosaurs basically, they started dominating the land around 250 million years ago. You have in environment, if we get an opportunity, we'll talk about the various phases of extinction where dinosaurs, they basically started dominating the land at a point of time when all the other giants at that point of time were already extinct, and dinosaurs took to the land. They started dominating the land, and it was during the time of the dinosaurs when things started moving away. It is said, we do know by evidences now, that it was during the time of dinosaurs, and dinosaurs had come into existence, and there was some such amount of variation that dinosaurs, they were the only species who had the variations which could take up to the skies as well, who could be herbivores, carnivores as well. So when the land basically got divided, dinosaurs were left in each of these lands, and then they dominated. And did they dominate the land? They dominated the world around us for close to around 200 million years. Again, as I told you in the first class itself, had there not been an asteroid impact 65 million years ago, you and I would not have been in existence. Dinosaurs would be roaming this planet even today. And they were one of the most evolved hunters that the world had seen. But nonetheless, here, this westward drift, as per Wagner, westward drift of continents, and then you basically had movement away from the poles. Away from poles. In German, he talked about the movement away from the poles. He referred to this as Polflucht, which basically, if you take an exact literal translation of it, it comes out to be flight away from the poles. Okay, do we still find the remains of them? Yes, that is how we have the evidence. What could be the reason for such large body size? The sudden dominance and increase in oxygen in the atmosphere that allowed the metabolism rate to increase exponentially, where they could support the large body structure and large body size, and also the kind of temperature which was prevalent. It was very hot at that point of time. So it was basically the temperature in different areas supported the growth of larger species. But then he said about the drift, about the westward drift of the continents and the movement away from the poles. Now, in order to support or cite the reasons, he made certain assumptions. So, assumptions, what were the assumptions made by Wagner? Ankush, for your question that why is it that the continents appear to be like inverted triangle, it is how the land broke away. And when you study about how the land actually breaks away with the help of plate tectonics, you will get an answer about that. Assumptions made by Wagner. So he was not an expert about the interior of the planet. So he basically made an assumption. He said, continents, which he referred to as Sial. Sial basically means silica and aluminium, right? That is what he referred to as the continents. Float and move freely over oceans. And he referred to the oceans and the ocean bottom as Sima, silica and magnesium. He further went on to say, just like a boat floats on water. So, just like a boat floats on water. So, how does and why does a boat tend to float on water? Basically, you would have read about Archimedes in your class 6th or 7th standard. Archimedes principle, which basically means that whenever there is a kind of a flotation, right, anything which floats, there is a force of buoyancy. There's a force of buoyancy which keeps it floating. So if, let's suppose, you are unable to imagine that force of buoyancy, think about it, a piece of thermocol, and thermocol floats on water. It doesn't sink in water. If ever you try to push that thermocol to the bottom of the bucket, you leave your hand, again that thermocol comes up and starts floating back up again, right? So that is what? That is the force of buoyancy, which makes it move upwards. And also, and as per this assumption, it means that the continents are moving freely. So as per this, you had two implications. Implications were, first of all, continents could move freely without any resistance. And secondly, continents experienced a force of buoyancy. Now, with these assumptions, he basically used these assumptions to solve the problem about these two movements. So now let us take a look at what are the reasons that he cited. So the first reason that he cited to support the westward drift explanation that he provided, it is not my explanation, it is Wagner's explanation, which was eventually rejected. Explanation for westward drift. Because he was convinced that, look, North America was joined with Europe, South America was joined with Africa, Pacific Ocean, Atlantic Ocean has come into existence very recently. Explanation of the westward drift. So, he said gravitational pull of sun and moon. So how was that responsible? How is it that the gravitational pull could basically lead to the westward drift? Listen to this carefully, try to understand it. This is planet Earth. And this was again Wagner's explanation. Okay? And on one side you have Sun. Now, he said that look, the continents were joined together and the continents would be rotating, or the planet would be rotating in a continuous west to east direction. Continuous west to east motion would be observed in the planet. But the gravitational pull from the moon and the sun would be so strong. While that gravitational pull would not be enough to move the earth in itself, to hold the earth in its place itself, but definitely that gravitational pull would be enough to hold the continents in their place. So basically, what did that mean? That meant as the planet, let's suppose this represents a continent, so as the planet would be rotating, the continents would be left in its own place and the planet would rotate. So as the planet would rotate and the continents being left in its place means what? You are observing what? See, this is the west to east motion. West to east motion is happening and the continents are left in their own place. So what is the motion of the continents if you take a look from the ground surface? So as the continents are held in their own place and rest of the planet is rotating, so it would appear that the planets are drifting in the westward direction. Right? So he said that gravitational pull of the sun and the moon were so strong, it held the continents in their own place. As the planet would rotate. Because remember, he talked about the fact that the continents are freely floating. Planet would rotate underneath them. Okay, so basically, the planet would end up rotating underneath them. That is where they would consistently be rotating, and the continents would be held in their place, and the planets would be rotating underneath them. Right? So, if let's suppose you are an individual standing here, and the continent, Patel, now take a look at it carefully. Okay, I think it's Twisha, right? So, basically, think about it that here you have the continent, you are standing here, and the continent is being held in its own place and the planet is rotating. So for you, what will be the direction of motion for the continents? For you who's standing on the planet, the continent would appear to be drifting westward, isn't it? So that is where he said that this is the reason why, because of that tidal force, he referred to this as a tidal force. Because of that tidal force, the continents would be held in their own place, and it would appear that they are drifting westward. But what is the reality? The reality is it is incorrect. Had the gravitational pull extended by the sun and the moon be so strong, had the sun and the moon and the lunar forces would be so very strong, the rotation of the planet would have stopped within 50,000 years. But that is not the case. The planet is still rotating. So obviously, that is not true. That is not correct. Okay. So that is basically what he postulated, what he said. Okay. So imagine here, everybody has understood this. Is there an issue in understanding this? Any issue? No? Understood? Okay. I'm going to repeat it once more. Think about it now. So he said that the continents are freely floating. I would say, don't judge it by today's principle that how can it happen? Obviously, this was incorrect. So basically, suppose this is the Laurasia, this is your region of Gondwana land. Now, the planet is consistently rotating, but the continents are being held. So that is where the entirety of the continent cannot be held. Maybe it will break. As it breaks, the remaining portion will start drifting away. The remaining portion will start drifting away, but this portion would be held by the moon and the sun. So if you are an individual standing here, for you, what will be the motion for this particular continent? Won't you see this continent to be moving in a westward direction on yourself? Is that understood? Is that imaginable now? Garima, then Sonu, is that understood now? Okay. So basically, in reality, this is not correct, because had the gravitational pull of the sun and the moon are not that strong. Had the gravitational pull been so very strong, the entire rotation of planet in itself would have stopped. But basically, the planet continues to rotate. So obviously, the gravitational pull of attraction is not that strong. So this is incorrect. Second reason that he cited was to explain the movement away from the poles. Explanation for movement away from poles. Away from poles. Okay. Or what is referred to as a flight away from poles or pole flight. So basically, he said that look, planet Earth is not a perfect sphere. Okay. It is not a perfect sphere, it is slightly bulged around the region of equator. Slightly bulged around the region of equator. Now, as the planet Earth rotates on its axis, there will be centrifugal force. I hope we are aware what is a centrifugal force. So what is a centrifugal force? When any object moves in a kind of a circular motion, any object moves in a kind of a circular motion, it will experience a force away from center. That is a centrifugal force. For example, let's suppose you tie a ball to a string and you rotate that string with your hands. You will experience that force where the ball will try to move away from you as you try to rotate. So that is the centrifugal force. Now, planet Earth is consistently rotating. Speed of rotation is highest where? Where is the speed of rotation is highest? Good. Equator, isn't it? The speed of rotation is always going to be highest at equator, right? So because the speed of rotation is going to be highest, there is going to be the centrifugal force which will act in outward direction here. Again, remember, he said that the continents are freely floating. So if they are freely floating, they will be impacted by that centrifugal force. So, as per him, continents experienced two forces simultaneously. As per Wagner, continents experienced two forces. What was that? One was the centrifugal force, or centrifugal force is the force acting away from center. Other was force of buoyancy. Okay, one was the centrifugal force, other was the force of buoyancy. Okay, now in this case, in this particular situation, think about it. Force of buoyancy pushing you upwards, centrifugal force attracting you towards equator because the centrifugal force is acting away from equator. So all the, let's suppose you have a continent here. Now that continent would basically be attracted towards this. This would be the force. If you have a continent here, that would be attracted like this. That is why the continents around the region of the poles, they started breaking up and they started moving towards equator. Okay, so because of a combination of these two forces, he said that the continents would basically break up and they would be concentrating around the region of equator. Now, was this correct? No, absolutely not. It is very, very incorrect. Why? Because, first of all, the continents are not your freely floating boats on water. Continents are giant land masses who have a connectivity to the mantle as well. You cannot expect the continents to be floating like boats. So that is simply not possible. And secondly, even if the continents would be floating like this, still, all of them cannot simply accumulate at the region of equator. When we talk about the region such as India, it has moved from the region of southern hemisphere to north of equator. If that would have been the case, India would never have moved to the north of equator. If that would have been the case, Britain, Russia, they would have never moved to that area. For example, Britain, if I give you a kind of a detail of it, Britain is very rich in coal, very rich. And the coal deposits of Britain, if you analyze them, they give you an idea, they give you an implication that this coal would have been created as a result of deposition of trees, which would be present in the tropical and equatorial areas. Same is the case with the coal seams in Russia also. They also, the trees which would have formed that coal, the evidence indicates to us that they would have moved, or these were the trees which at one point of time would be present around the region of equator. So clearly, region of Britain, etc., they have moved northwards. If this would have been true, all the continents would have, all of them would have accumulated only around the region of equator. So because this was incorrect, along with the reasons and along with the assumption, that is where Wagner went incorrect. And due to this, the entire theory was junked. The entire theory was trashed. Nobody at that point of time gave any importance to the fact that what Wagner was actually saying with respect to the drift, that drift could indeed happen. Fair enough, the reason was not correct, but that drift could actually happen. Nobody thought about it in that direction. Everybody concentrated about ridiculing Wagner, ridiculing Germans, ridiculing German scientists, and so on. So, in that ridicule, Wagner was ostracized, he was defamed, and he left all of this. He continued with his own solemn journey and his own study about the ice sheets of Greenland and studying about the climate change. It is during this when he died, a kind of an inglorious death. where Wagner basically died as an individual. At the time of his death, there was more fun made of Wagner than anybody who could recognize the good work that he had done. And the irony of the matter is that his theory was rejected based upon the incorrect reasons that he provided. 50 years later, 50 to 60 years later, when American scientists they presented the plate tectonic theory, the reasons were not very clear that why that plate tectonics is happening. But still that theory was accepted. It is a theory that we still accept even today. So that is why I told you, many of the times in the scientific community, you have to be aware of where that scientific theory is coming from. When the same kind of postulation is provided where the reason is not very well known, but I can see its impact, and I'll tell you that impact which is happening. For Wagner, it was not a correct standard, but for the Americans, it was the correct standard. They were celebrated. Princeton and the various different celebrated universities, they basically celebrated all of these scientists who provided the plate tectonic theory based upon the same ideals that Wagner worked upon. But now we can say that it was the theory of continental drift which paved the way for that understanding that the continents indeed could move, and they could move from one place to another. Okay, so that is about the theory of continental drift, the reasons, the evidences, and why that theory was eventually rejected. Okay, now don't you think it might have happened with the principle of inertia? Yes, eventually, Prem, you have to understand that once that gravitational pull of attraction happens, and as per Wagner, if basically he tells you that if the continental landmass was held in its place, then inertia would take over. But we know that that is not the reason why the continents do move. There's a whole together different reason, and that is associated with what is present in the interior of the planet Earth. Centripetal force is not clear. We have not even talked about centripetal force. Why do you want to understand centripetal force? We have talked about centrifugal force. Centrifugal force is the force acting away from center. Listen to this carefully. If ever you have tried to ride a bicycle in consistent rounded circles, ever, you would feel basically, if you have tried to do that, rather than the common logic which will tell you that you will fall towards the center of the circle, if you have done that, you will, if you have ever fallen in that experiment, you would always fall outside. You would have experienced this. If not, try doing that. Obviously save yourself. But if you try doing that in moving in a consistent circle, you tend to fall outwards. If you take a string and attach a ball to the end of the string, you try to rotate that string with your arms, basically you will find that you will get a force where the ball will try to move away from you, where it will appear that the ball will simply fly away from you. Try doing that. That is the force acting away from center in a rotational motion. That is centrifugal force. Okay, right? In future, after uh, in future, after millions of years, can there be a chance to grow new continents? Absolutely, yes. Why not? So other continents moved towards equator due to centrifugal force, but what prevented poles from moving towards equator? Wagner was very consistent that in the fact that around the region of Antarctica, all the continents were surrounding Antarctica. All these continents separated from Antarctica because of these forces. Because Antarctica was at the region of the poles, so it could not be impacted by centrifugal force. Okay. Now, that is the case of the continental drift theory. Now, after this is the kind of a previous year question which was asked. So we will discuss this and then we will move on into the convection current theory. So here, basically, the question which was asked and which has been repeated by UPSC multiple times. What do you understand by the theory of continental drift? Discuss the prominent evidences in its support. So, when we talk about so how do you answer this question? So, when you answer this question in the intro, always, when you have two sets of questions, always in the introduction, answer the main question. What do you understand by the theory of continental drift? So, in the introduction, you will write theory of continental drift postulated by Alfred Wagner talks about the existence of a supercontinent named Pangaea, and then the movement of the other continents or the breakage of the supercontinent, and then the movement with respect to each other, leading to the present day shape of the continents and oceans. That's it. It has to be concluded. The introduction has to be encompassed within 30 to 35 words. That's it. Okay. So that is where you write the intro about continental drift. Then comes the body. How do you start the body? Body should always have a natural flow from the portion of the intro itself. It should be you should not have the evaluator scratching their head that okay, what suddenly there is a break. No, it should be natural. So basically here, the theory provided by Alfred Wagner was based upon set of varying evidences from paleontological to geological. Then the question is only asking you about the evidences. So some of the prominent evidences. In mains, the pattern of questions are repeated, Mehtab. Yes. So the evidences, you divide it into jigsaw, fit, geological evidence, right? Glacial evidence, and write a couple of sentences or 3 to 4 sentences about it. Draw as many drawings and diagrams as possible. For every answer of geography, you have to draw a diagram. Don't think about it that this is a simple diagram. What will I draw? The evaluator would know it naturally. Fair enough. Let the evaluator know. But the purpose of drawing is if you draw something, even if it is not a good depiction, it provides that variation from the written text. And even if your written portion is, let's suppose, grammatically incorrect, or maybe you are not able to factually represent that, your drawing will do the talking. So that is where that drawing is essential. Be it a very representative and a kind of a customary drawing, it has to be drawn. For example, in the jigsaw fit, simply draw a rough map of, let's suppose, South America and the region of western portion of Africa. Just draw that. It need not be accurate, but it will do the job. That's it. Even if you do this much, it takes you 5 to 6 seconds. More than enough. Okay? Then eventually, it is a 10 marker question, so you don't have to talk about the reasons here. Conclusion, you can simply talk about the theory of continental drift was rejected because of the incorrect reasons cited by Alfred Wagner. But then, this theory paved the way for our better understanding of the surface and the earth, and paved the way for the postulation of theories in the future, such as the plate tectonics, which ably are able to explain the present movement of the continents and oceans. That's it. So, in this way, you are showing continental drift theory in a positive light, at the same time highlighting that it was rejected. Okay, so it was rejected because you had the concept of, you had the incorrect reasons that he cited, but at the same time, he did some good work. Okay, right? No, glacial evidence not needed to be drawn in that case, but I'm saying that for every answer, at least one or two diagrams need to be drawn for every answer. You should have the ability to draw. In fact, I will always move ahead to also tell you that your answer writing in geography, those of the candidates who are able to write good answers in geography, I have never come across any candidate who has written good answer in geography getting less marks in the entirety of the mains. Because geography answer writing teaches you how to be descriptive and ensure good presentation with the images. So that will allow you to form flow charts, block diagrams, etc. Even in the case of polity, governance, sometimes even in art and culture, economics, more importantly, ethics, essay writing also sometimes. So not so much in essay writing, but in the GS4 and 1 to 4 GS subjects. So I have always seen in my past experience, I can vouch this with a kind of a certainty that always it is the case that if you are writing good answers in geography, I can give you a guarantee, you will score good in all the various answers, because then you would basically know how to explore that answer writing. You will be exploring and pushing the limits. Okay, right? So keep that in mind. Now, Mega, how to link answers with newspaper data? Wait for it. Wait for it, my dear friend. Wait, have patience for around 10 to 15 classes. You will develop that approach on your own. I'm not going anywhere before 24 classes. I hope neither are you. Have patience. Now, we talk about the case of convection current theory. What is this convection current theory? So, this was provided in the 1920s, 1919 onwards, by one of the proponents who basically, in his studies, he actually took physics as his area of expertise, but eventually he veered towards the portion of geography. It was that individual who is credited with the development and the detailed development of radiocarbon dating, which helps us find the evidence and the age of the rocks and the fossils as well. So this was provided. Is the continent still drifting? Absolutely, yes. India is still moving northwards. Africa is moving northwards. Africa is breaking into two. North America and South America, they are indeed moving westwards. So the continents are moving. Australia is moving in a northeastern direction. So, yes, the continents are indeed moving. In the near future, you will find that the Mediterranean Sea will disappear because Africa will collide with Europe, and there, instead of the Mediterranean Sea, you will have mountains just like the Himalayas, maybe taller than them. So the continents are moving. And by near future, again, understand, we are talking about maybe 100 million years or 150 million years from now. So this theory was provided by Sir Arthur Holmes. Why I do need to specify the time, I would have told this to many of you. Basically, when in one of the classes, I told the candidates that there's a fourth range of Himalaya coming up in the northern portion of Uttar Pradesh and Bihar in the coming years. One of the students, they wrote a long mail that could you support this, because my father recently bought a piece of land there, and if Himalayan ranges are coming there, that means our money has gone to waste. So just so that you don't panic, it is not going to happen in your lifetime. Maybe we humans, we don't exist till that point of time, but basically that is how the movement happens. Okay, so this was the convection current theory. This was provided by Arthur Holmes, and it works. He basically said that heat from the inside the Earth's surface, that gets transmitted to the surface with the help of convection current. Now, what is a convection current? So basically, you would have seen, ever if you have boiled a pot of water or milk, in case you have not done this in your life till now, high point in your life to do this? If, let's suppose, you try to boil water or milk. Now, what is it that you experience? Is it the case that straight away the bubbles start forming on top of water? No. Initially, if you have noticed carefully, you will find that small bubbles, they start forming at the base. Bubbles basically means water is getting converted into steam, into vapor. Small bubbles, they start getting created at the base because that base is getting heated up. Then these bubbles, they start rising up. They start to rise up. They reach the surface. Meanwhile, the colder water from the sides, they replace this. Portion which has risen up, they replace this. So in a way, heat is transmitted by the motion of water. Heat is transmitted by the motion here, movement of particles. So convection current, when we talk about convection current in its entirety, this is transfer of heat due to the motion of particles. The hotter particles, they rise up, the colder particles, they settle down, they sink down, and that is where the heat basically gets transmitted. Now, when we talk about this convection current here, basically, what is it that he said? He said that, look, when we talk about the Earth's crust, beneath the Earth crust, you have the mantle, you have the portion of mantle. Now, in the region of mantle and at the region of the Gutenberg discontinuity, let's suppose here this is the Gutenberg discontinuity. Gutenberg discontinuity. Now there is heat which is provided from the region of the outer core. The residual heat keeps on getting supplied from the region of the outer core continuously, isn't it? So as this heat, residual heat gets supplied from here, what it will do? It will immediately melt the portion of mantle. That excess heat will melt that portion of mantle. Now, which is lighter, liquid or solid mantle? Which will be lighter? Apply logic here. Which will be lighter? Liquid, right? So liquid will be lighter. Being lighter means it will try to rise up. So that is where basically it will try to rise up. The molten portions, they will melt the areas immediately above it and they will start rising up. Meanwhile, in this portion, there is some amount of vacancy created. So the cold, just like the convection current, the colder solid mantle, that will replace this. Again, that will also get heated up. So it will melt. Molten portion will melt the area above it. It will tend to rise. More molten portion will tend to rise. More molten portion will tend to rise. All the meanwhile, the solid particles from the surrounding, they will start replacing the risen portion. So that is when it will rise up. And you will have a convection current. You will have a convection current. So mantle is solid. Mind you, mantle is solid, but then you will have the situation where, due to that immense residual heat at the region of the Gutenberg discontinuity, due to that immense amount of heat, this portion will start melting. It will melt the region above it. It will try to rise up. It is liquid. It will try to rise up. More heat, more portions will be melted, more rising up, more portion will be. And in the meanwhile, the solid substances will replace it. Because mantle, as I gave you the analogy yesterday, in case you remember, basically I told you that mantle is like the pulp of coconut. If you have to think about it, that it is solid, but if you press it, it can be compressed, it can be deformed as well, right? So the solid portions will replace it, it will melt, it will rise up. He said this is how heat from the interior gets transmitted outside, outwards. Garima, are you aware about the how many of us are not aware about discontinuities at all? Okay, right. So I would suggest to you, kindly take a look at the recording of yesterday's class. Clearly, you have not attended the class yesterday. Take a look at that. There we have talked about the portion of discontinuities. Discontinuities, they are a zone of differentiation in between different areas. So this talks about transmission of heat from interior to the outside. Okay, transmission of heat from the interior to the outside. So this is your mantle, this is your core, outer core, which is molten. Now this convection current will have two components, vertical component as well as horizontal component. Now, he also said that this convection current can come into existence even in the region of asthenosphere. Asthenosphere is also in a semi-molten state. So there also it can come into existence. But we'll study in detail about that because clearly there is no point rushing into it. We will talk about it in detail in the next class. This is where we'll end the session here today. I hope that till now you are comfortable and just revise this portion before you come for the next class. Then you will be able to cover the portion of the plate tectonics also easily well. Okay. With that, we'll end the session here today. Any kind of question? Okay, let me give you certain areas for map pointing. Good. Certain areas for map pointing. Point it out in the atlas. In case you are not able to find it in the atlas, take the help of Google. So here, first of all, I want you to locate certain mountains. Appalachians, Brooks Range, Rockies, coastal ranges, Andes, Sierra Madre, Oriental and Occidental, Alps, Atlas, Ural, Caucasus, Then Himalayas, all of you know, Karakoram, Great Dividing Range, and locate some of the trenches, oceanic trenches. These will be the dark blue areas in the world map in the oceans. Mariana Trench, the deepest trench. Then Kurile Trench, Peru-Chile Trench. If you locate these areas before coming to the class, your understanding of plate tectonics will be much better. Japan Trench, Sunda Trench. Trenches are the deepest portions in the oceans, narrow, deeper portions in the oceans. Okay? Locate these areas, find out the regions around it, and then we meet again in the next session where we continue further. We discover more about this subject. That shall be all from my side, and we meet again. Do take care of yourself. Goodbye. Thank you.